Okay, we're going to start with arc length of a parametric curve. So I want to go back to what we did in the last video. In the last video, we looked at the speed of a particle. And the speed of the particle that we looked at in particular was this one, where we knew it was 2 units to the left. This is not to scale, 1 unit up. And what we found was the magnitude, or the length of this vector triangle, so that hypotenuse was the square root of 5. Well, imagine if we did an infinite number of these vector triangles along the parametric curve, and we found the length of the hypotenuse all along that curve. If we add all of those lengths together, we would get the arc length. So this isn't anything that's much different than what we've been doing before. So what we would say is, if we find that speed, if we find that length of the hypotenuse, that's x prime of t squared, plus y prime of t squared. And if we integrate that over an interval from a to b, now we have the length of a curve on an interval from a to b. So the length of a parametric curve, not how you spell parametric, on the interval from a to b is this. Okay, I'm not going to do an example on this one. Oh, I take it back. Let's do an example. Sorry, I forgot that I did put one. Let's do an example. We're going to find the arc length of the curve defined by this. X of t is 3 cosine t, y of t is 3 sine t, so let's do some math here. We're going to find the arc length from 0 to pi. All right, first thing I need to find is x prime of t. The derivative of 3 cosine t is negative 3 sine t. The derivative of y prime of t is 3 cosine t. I'm going to find this length from 0 to pi, so I'm going to integrate from 0 to pi the square root of negative 3 sine t squared plus 3 cosine t squared. If I square each of those, I get 9 sine squared t plus 9 cosine squared t. Hopefully you're thinking about Pythagorean, or the Pythagorean identities, so trig identities. We know sine squared plus cosine squared. So if I factor out a 9 from these, if I factor 9 out of both of those, I get sine squared t plus cosine squared t. And I know that, and you should too, that sine squared plus cosine squared is 1. So this ends up just being the square root of 9, or just 3. So that's kind of cool, because the antiderivative of that is pretty straightforward. That's 3t. And if we evaluate that from 0 to pi, I end up with 3 pi as the length of that curve. Kind of nice. Okay, now let's go on to the last idea. And the last idea is surface area of a parametric solid of revolution. So let's take a look at this first one. Or let's just take a look at this. The surface area. We know that surface area of a cylinder, so this is going to be the same thing. We're still putting cylinders inside. So if we're going to look at the surface area of any cylinder, that's 2 pi RH. And we've looked before at surface area. In this case, H is arc length. So remember when we found the surface area, the height of each of the cylinders, we're measuring, we're on the curve itself. So the height of each one is the arc length of that curve on that interval. So let's find this, write down the surface area then of a solid of revolution for this parametric equation, or for any function, would be from A to B, from whatever our interval is. I'm going to pull the 2 pi out, and this would be the radius times the arc length. And the arc length, we just looked at it. That was the square root of x prime of t squared plus y prime of t squared. Let's talk about this radius. If I have, let's just say, a parametric equation, let's just say here's my parametric equation, and I want to rotate that around the y-axis. So when I rotate that about the y-axis, I have a radius that is horizontal. So since we're looking at a parametric equation, in order to figure out what that radius is, I need the horizontal component of my parametric equation. So in this case, since we're rotating around the y-axis, the radius will be x of t. So in this case where we're going to rotate about something vertical, I would have 2 pi from A to B. R in this case is going to be x of t. And then to save some time, so you don't have to watch me rewrite this a million times, I'm going to copy this and paste it down here. So this is if the axis of rotation is the y-axis. You're not going to see it be anything other than the y-axis. So we're not going to talk too much more about that. Okay, now let's talk about if we rotate about something horizontal. So if we're going to rotate that same function about the x-axis instead. So here's my parametric equation. I'm going to rotate it around the x-axis. And in this case, the radius is going to be y of t. The y component, the vertical component. So I would have 2 pi from A to B, y of t, and then, oops, the arc length. I ran out of space. Let me move it all over a little bit and make it a little smaller. Okay, and that's if we're rotating around the x-axis. And we're not going to do anything more, anything crazier than the x and the y-axis. Rotation is the x-axis. Okay, let's try one. We're going to find the surface area generated when the plane curve defined by blah and blah is revolved around the x-axis. So I don't even really have to draw this one because we already know the x component and the y component. We can find the arc length. So this one's going to be pretty straightforward. We don't even have to draw it, which goes against everything I've ever told you. But because we're just rotating around the x-axis and because this is parametric, we know everything we need to know. Okay, so let's first of all find the radius. We're revolving this around the x-axis, so the radius is going to be vertical. The radius is going to be the y of t value in this case, and that's t squared. The height is the arc length. I don't know why I'm a glutton for continually rewriting this, but it's good to see it over and over. So there's the height. So in this case, it's going to be the square root of x prime of t, which is 3t squared plus, squared, plus y prime of t, so that's 2t squared, if we combine this or we simplify a little bit, that's 9t to the fourth plus 4t squared. Okay, let's put this all together then. We're going to find the surface area. So this is going to be from 0 to 1. The radius is t squared. And I have 9t to the fourth plus 4t squared. Let's see if I can simplify this at all. I can see that under the radical, they both have a t squared in common. So if I factor out a t squared, I'm left with 9t squared plus 4. I can separate those two into two different radicals. So I can write this as the square root of t squared multiplied by the square root of 9t squared, or 9t squared plus 4. And I know the square root of t squared will just be t, so this ends up being t cubed. I'm going to stop here because, honestly, you're not going to see much more than this. You'll be seeing just setting it up and not calculating. So at this point, now that you've got it simplified, because it could be which of these, multiple choice question, which of these would be the setup for the surface area of a parametric revolved around the x-axis. And so knowing how to simplify a little bit is important. From here, you can just plug that into your calculator and get a solution. Don't have my calculator on me, unfortunately, but you can plug that in. Leave 2 pi in your answer, so it'll be 2 pi times whatever you get for the antiderivative from 0 to 1. Okay, that's the discussion of calculus for parametrics. We'll talk more tomorrow.